welcome to Analog VLSI Design. This is lecture 2. So in the previous lecture, we tried to see what exactly we want out of this course in the context of an amplifier design. Then we saw that we want to design an amplifier that amplifies power, and then we also saw that this is different from a voltage right, and we saw it with an example of a transformer. A transformer can act as a voltage amplifier, but it's not a power amplifier because a transformer is a passive device, and obviously a passive network can only pass on the power that it receives in the if the passive network in question is lossless, right? If the passive network in question is lossy, then obviously it cannot even do that. So it will consume some power, and the power that will be delivered to the load will be lesser than the power that you are extracting from the source, and that is our good old power consumption or law of conservation of energy, right? Okay, so this is something that we motivated for half of lecture 1, and while we were closing in at the end of lecture 1, we were also trying to see what aspects a network must have if its output voltage is largely independent of the load resistance that it is driving. So this was the question. This was the question that we were delving into when we stopped at lecture 1, right? And the example that we were concentrating on was the following. So let's say I have a supply VDD, and let's assume it's a ideal supply with no internal resistance. If it doesn't have an internal resistance, it effectively has an infinite driving capacity. Now we said that we wanted, if this is equal to 2 volt, and we wanted a 1 volt output, right? If we wanted a 1 volt output, and then we said that this can be easily be achieved by making a voltage divider using a resistor divider stack, and we will be observing the voltage at the location marked. However, now what happens if I connect a resistance RL, because ultimately when you are making some network, you are making the network in order to drive something, right? There's no point in making a network which cannot drive a load. So all networks, all electrical networks that we make is made with the purpose of driving something. So in this case, we said that what if this network is supposed to drive an RL, and on top of that we would want this voltage V0 to be approximately equal to VDD by 2 for 1 volt. Then what is the constraint on RL and R and so on, right? So we did this from the perspective of output resistance, and I hope you have also done it from the perspective of figuring out the total resistance or the total V0, right? And then I'm sure we came to the same conclusion. Now, the curious among you might also have gotten a third way of looking at it, and let me spend a couple of minutes on that third way. And the third way is that of if I use Thevenin's theorem, or if I rather Thevenize this circuit in the box, right? If I Thevenize this circuit in the box, right, and I try to Thevenize the circuit looking from this port, right? If I try to Thevenize the circuit looking from this port, what should I get? What will be the Thevenin equivalent network? The Thevenin equivalent network will be the same network, or in other words, how do I derive a Thevenin equivalent network? In order to derive a Thevenin equivalent voltage, I'll have to remove the load that is connected between the ports, and I'll have to find out the voltage. So this voltage will be my Thevenin equivalent voltage, and what will be the Thevenin equivalent resistance, right? To find out the Thevenin equivalent resistance, again we'll have to remove RL. Right? We'll remove RL, and what we do next? We desensitize or de-energize all the voltage sources. That is, we set all the voltage sources to 0. If there were current sources, we had to set the current sources to 0. So setting a voltage source to 0 is equivalent to short circuiting the voltage source. Setting a current source to 0 is equivalent to open circuiting a current source. In this network, we have a voltage source, so we short circuit the voltage source, right? And if we short circuit the voltage source, what do we end up with? We end up with this network, and what is the effective impedance looking in? The effective impedance looking in is nothing but parallel combination of R and R, which is R by 2, right? So this is RTH, the Thevenin equivalent resistance is R by 2. So now that we have both the Thevenin equivalent voltage and Thevenin resistance, how do I modify this, or how do I redraw this circuit? I can replace this circuit, which is Thevenin equivalent, which will be nothing but a Thevenin equivalent voltage source, a Thevenin equivalent currents, Thevenin equivalent resistance, and these are my output ports. So this is equivalent to the output ports of the network, and my RL gets connected here, and the voltage that I will observe across RL, right, the voltage that I will observe across RL is identical to the voltage that I will observe across RL in the original network, right? So in our case, what is VTH? In our case, VTH is 1 volt. What is RTH? RTH is R by 2, right? So now let's go to the next page, and if I redraw the Thevenin equivalent network, what do I get? So this is VDD by 2, this is RTH, this is V0, this is RL, right? So what is V0? V0 is VDD by 2 times RL by RL plus RTH. So for V0 to be almost equal to VDD by 2. What do I need to satisfy? We need to satisfy that RTH has to be much less than RL. And if RL has a range that is RL can have a minimum value and a maximum value, what should RTH be? Your RTH should be less than RL min. Correct? And in the example that we had taken, RL, the range of RL was going from 100 ohm to 100 kilo ohm. So if we were in charge of finding out the values of R, right, what should have been my constraint? My constraint would have been RTH should have been much less than 100 ohms, or in other words, RTH is R by 2. So R by 2 should have been much less than 100 ohms, which implies that R should have been much lesser than 200 ohms, right? So if you can ensure that R is much lesser than 200 ohms, then you are all set. You can ensure that the output voltage V0 for this network, will remain at approximately VDD by 2 for the entire range of RL. Okay. This is so far so good, but is there an issue that you foresee with this type of implementation? There is indeed an issue, and the issue is as follows. Now let's go back to the original circuit that we started off with. So let's say this is 2 volt, this is RL, and we sized R to be much less than 100 ohm. Let's say we sized R to be 10 ohms. Okay. So now what do you think is the power consumption of this network? Or in other words, what do you think is the current that I am drawing from the battery? Now note that these 10 ohms are hard coded, right? You are not changing these 10 ohms. So when RL is, let's say, 100 kilo ohm, right? When RL is 100 kilo ohm, the effective resistance that you are seeing, right? The effective resistance that this battery is seeing is 20 ohms, because you can essentially neglect RL, right? So what is the approximate current that you are drawing? The approximate current that you are drawing is 2 volt by 20 ohms, right? So this is approximately equal to 100 milliamps. So note that regardless of the value of RL, right? Regardless of the value of RL, you will at least be drawing 100 milliamps through the battery. And this is for maximum value of RL. If RL reduces, you will be drawing more current, maybe slightly more than 100 milliamps. But the key point to note here is that whether you have an RL or not, in order to ensure that the entire range of RL is satisfied, you will have to always draw 100 milliamps of current. But out of this 100 milliamps, how much current is actually going into RL? So what is IRL? IRL is approximately equal to this voltage V0, or rather IRL is equal to V0 over RL, and V0 is approximately equal to 1 volt, right? That's what we designed it for. So essentially this is 1 volt by RL, and since RL varies from 100 ohms to 100 kilo ohms, so IRL varies between when RL is 100 kilo ohms, the amount of current that IRL is drawing is 1 volt by 100 kilo ohm, and when RL is 100 ohms, the amount of current it's drawing is 1 volt by 100 ohms. So this is nothing but 10 milliamps, and on the other side this is 10 microamps, right? So essentially the load current for which you have designed this circuit is supposed to be varying between 10 microamp and 10 milliamps. However, in order to support this load current, you are always drawing at least 100 milliamp current from the supply. So what percentage of the supply current is actually going into your load? Only maximum 10% of the supply current is going into the load, and the 90% is getting wasted, right? So clearly this is not a feasible solution, or this is not a very power efficient way of making a voltage regulator, right? Or rather a more efficient way of expressing the problem here is the fact that this is a power hungry way of setting up a voltage regulator which can accommodate a variety of loads. Now why am I harping on this? I'm harping on this because even though we are not at that stage of the course, can you intuitively think of a solution? Can you intuitively think of a architecture which can help mitigate this problem? Mind you, I am not asking for a final architecture. I am asking you to put yourselves in the shoes of a designer and think, if this is the problem, what can be the potential solution? Think for a moment and we'll come back.